The next topic we will cover is reactive power flow in some simple networks. Really just to look at how the various devices can work together in some very basic networks, and then we'll zoom down in more detail and look at more particulars on each of those devices, and then we'll look at how they work together at more complicated networks towards the end of this whole module. So our objectives here are for you to be able to describe reactive sources and describe reactive loads, how shunt capacitors can be applied, and then consider the megawatt flow across a transmission line and how that can vary with the angle difference as well as the voltage magnitude difference. We'll look at the megawatt characteristics of transmission lines as they are loaded up, how they go from being capacitors at light load to inductors at heavy load. We'll then cover a very brief introduction to voltage collapse. But voltage collapse is this whole thing that's always lurking out there. Most of the time, your job as a voltage controller is pretty straightforward. You bring on the capacitors in the morning, you take them off in the evening, you bring on the reactors in the evening. But underlying that, there's always the threat that under heavy load conditions, your system could just go into voltage collapse. So we'll give a preview of that, and then we'll go into that in a lot more depth at the end of this whole segment. And then we'll discuss causes of low voltage. So basically, your reactive sources are two types that can be dynamic or static. By dynamic, we mean that reactive source will respond pretty much instantly under its own control to accommodate changes in your system. Primarily, we're looking at transmission line outages or losing a generator. When you have a transmission line outage, what happens is the load on that transmission line transfers to other transmission lines. They become more heavily loaded and they draw more megavolts. So you want dynamic sources like generators, static var control compensators, or a synchronous condenser is basically a generator without a prime mover. You've got a rotor and a stator, and it's rotating there, and it can go from being just like a generator, it can go from producing megavolts to absorbing megavolts. So time and again, your dynamic var sources are there to cover that next contingency. We've talked about the importance of managing your system to handle the next contingency. That's the benefit of dynamic var sources. As an operator, you don't have to do anything to get them into action. Whereas your static var sources, like shunt capacitors, even switch shunt capacitors, a switch shunt capacitor looks at a voltage difference, and when that voltage gets below a certain value, it actually switches. But that takes a few seconds, so we don't call that a dynamic var source. Or your transmission lines can produce VARs, or they can be absorbing VARs, and then your cables, generally they are high VAR producers. But they don't respond actively to help you when you have a contingency. And so again, a very popular question on the NERC exam is, which of this set of devices are a dynamic VAR source? Generators actually have to be in the automatic voltage regulator, automatic control mode to be dynamic. If that regulator is not on, then basically they are a static source. And so again, as an operator, you always have to be on top of making sure you understand that your generators are on automatic voltage regulation, and having the power plant operators notify you if for some reason that they're taking them off the automatic control mode. Now, certain devices provide a net inductive load on the system. The customer loads, like we talked about, and especially all the motors, are a reactive load. And so they create a net reactive demand on the system. Your shunt reactors are a reactive load. And again, they are primarily there to be on in the nighttime, or if you have a very high voltage, long transmission line, they can actually be on 24 hours a day to compensate for all the charging that comes from that transmission line. Your heavily loaded transmission lines, they provide a reactive load on the system. Your transformers, they have the magnetic windings, they're a reactive load. The generators for the most part are producing megavars to compensate for the loads, but there are certain times, especially during restoration or light load conditions, they can absorb megavars and they are a reactive load. Wind farms, we've talked about the very high penetration of wind. They are a net reactive load. A wind farm is basically like an induction generator. It's like an induction motor, but it's being driven by the wind, and the rotor is running faster than the actual AC voltage waveform. But they are net consumers of reactive power. So you'll often see wind farms tied in with static VAR compensators. DC lines, they have the rectifiers, and they are a net drawer of reactive power. And then synchronous condensers, for the most part, synchronous condensers will be producing megavars, but there are times when they can absorb and they are a reactive load. We talked previously about the direction of power flow, but it's important. A generator, when it is producing megavars to take care of the demand of an inductive load, and we have positive megavar flow in this direction, that generator can be referred to in a number of different ways. It can be called lagging. Now, it's lagging in terms of the fact that it's serving a lagging load, and the voltage is actually leading the current, or in terms of the current is actually lagging. So the voltage is actually ahead of the current. And so it's important to realize the reference that the generator is lagging, but that is in terms of the fact that that generator is now serving a lagging inductive load. So we can say that generator is pushing megavars onto the system. We call it boosting because in this mode it is actually helping raise the voltages. So the idea is when we're raising voltage, we call that boosting. When we're lowering voltages, we call that bucking. Or it's overexcited, and we'll see this later, that in order for this generator to push megavars onto the system, we actually have to increase the field current. That tends to increase the voltage. So again, it's important to understand that each of these terms means that this generator is actually putting megavars onto the system. On the other side, a generator can be leading, and in that particular case, it's in reference to the fact that that generator is serving a load where it's a leading load. In other words, the current for that load is leading the voltage. So of course, the current at this point is leading the voltage, and the current at this point is leading the voltage. And in this case, we are absorbing megavars. So we can call that in a pulling mode, pulling megavars off the system. We can call it bucking. We're lowering the voltage. There's a simplified term that says the megavars will flow downhill on the voltage. In other words, if we want to pull megavars into the system, we actually have to decrease the internal voltage of the generator. And so that's why it's bucking. We're actually lowering the voltage. And again, that goes along with being underexcited because we're actually decreasing the field current, we're decreasing the internal voltage, and we're pulling the megavars off the system. And again, for those preparing for the NERC test, you'll often get questions that ask you to understand which of these modes are applicable for different situations. Now, so in general, we have generators and we have loads which are inductive. So here we have 10 megavars coming out of this generation, pushing megavars onto the system. It's overexcited, it's working in a lagging mode, and it's boosting voltage. So the voltage here we would expect to be somewhat higher than the voltage here. Here is the nice beneficial effect of shunt capacitors. We switch on a shunt capacitor which has an equal megavar rating to our inductive load, and look what happens. That shunt capacitor totally compensates for that inductive load, and our reactive power goes to zero, our current in the line goes to zero, and we can now use that line for more beneficial purposes for sending megawatts. So in general, we want to put our shunt capacitors right close to where the inductive loads are located. Now, at this point, I'll get into the fundamental equations, okay? And we don't need to go into the derivation, okay? This in detailed math. But if you bear with me here, we are going to derive two fairly simple equations. The equation for the sending in megawatts and the equation for the sending in reactive power for a very simple circuit of a generator feeding a transmission line with a certain reactance into a large system. And again, we don't have to go through the details of the math, but I want you to understand, just as a preview, I want you to understand how the basic megawatts flow and the reactive power flows as we have a transmission line that is going through a heavily loaded situation. Now, if you don't like the math, let me use the mechanical analogy, all right? This is the angle at the sending end. This is the angle at the receiving end. This distance in the middle is the voltage magnitude across the line. And notice, as I advance my angle, the voltage at the middle of the line is dropping. I get to 90 degrees, and my voltage, I could actually work it out, it's actually 0.707, 1 over root 2 at 90 degrees. But then look what happens when I go to 180 degrees. My voltage at the middle of the line has gone to 0. So think about it. I've got a high voltage at this end, a high voltage at this end, voltage at the middle. What's going to be happening? I'm going to have a huge amount of current flow from both ends. All right? So that's the mechanical analogy. Now, if we do all the math, okay, then basically we find out that as we advance that angle from 0 to 180 degrees, my power is peaking at 90 and coming to 0, all right? I've got 0 voltage at the middle of the line, so I can't get any power flow, I can't get any megawatts down that line, can I? Because megawatts is voltage times current. But look at what is happening to my reactive power flow. It's starting out at 0 and it's coming on up, and the reactive power flow when I'm 180 degrees apart is huge, all right? And this is really important for you to understand that reactive power flow is drawing current, and that current will trip relays. Even though there are no faults on the system, as my rotors oscillate, I can have lines tripping out of service because we have huge reactive power flows and currents. So just, again, bear with me a little bit on the math, okay? And we'll just, for those of you who are moving on and are going to be getting into the power system analysis, this little part here is the fundamental part of power systems. If you've got a computer science background or electronics background, this is the heart of every load flow program. All right, so we'll just go through we won't actually go through the details, but I'll go through the principle of how these equations are derived, okay? Now, current is basically voltage divided by impedance, all right? In a DC circuit, if I have a 12-volt battery and I'm driving a 1 ohm load, I know that the current will be 12 volts divided by 1 ohm will be 12 amps. In an AC power system, we take that very same principle and we generalize it with complex numbers, okay? And again, we're not going to, so basically what we can say is that if I have two voltages here, a sending end voltage and a receiving end voltage, I take the difference between those in a complex plane, I actually get this vector here. We can represent that vector by the summation of this voltage difference here and this voltage here. I then divide that voltage by my impedance, which in this case, I only have a reactance. So the impedance of this, when we deal with complex numbers as electrical engineers, we say an impedance is the resistance plus J times the reactance. And again, this is what makes the math work out. And so basically what we're doing here is we're saying that the current in this line is this value here divided by J times the reactance of impedance. We're basically taking the current and we're saying it's the voltage difference, and this voltage difference here, if you'll just bear with me, basically is it's that voltage magnitude, the source voltage, minus this vector here times cosine of the angle. That magnitude there is that vector times cosine of the angle. So the voltage difference in this direction is Vs minus Vi times cosine of the angle, and that is that term right there. All right. So that's our voltage difference in this direction, that one there. And this voltage magnitude in this direction is Vi times sine of the angle. So without getting into a lot of detail, we can see that basically we've said that that's a complex number. That number there is basically this portion, is that portion, this, and now we have the J because we're going in a different direction, which is that value there. And so basically what we're doing is we're taking a voltage difference, dividing by impedance, and we're getting a current. And again, we won't go through all the detail, but that's the fundamental derivation. That and our complex power then, S, is the voltage times the current. Now we actually use a thing called that's a conjugate. And remember where we talked about how we have a lagging power factor where the voltage is lagging, but then we want that lagging current to produce a reactive power in that direction, because reactive power flows to loads. That's why we have to have this little symbol here. But from all of that, we basically are able to figure out for this little network, sending in voltage magnitude Vs, receiving in voltage magnitude Vr, and an angle. This is the way we represent angle, this little delta sign. Angle here is 0. Angle here is the delta. That's how we figure out the reactive power. And again, it's just a little bit of mathematical manipulation. But the bottom line is we really want to understand how the megawatts and the megavars flow as we vary the angle at this point and we vary the voltage magnitude.
We have a question. So could you equate that, because I see that S is important and you're showing the angles. It seems to me that that's also important to see how that causes power to move in one direction or the other. So maybe what would you see if the angles changed magnitude? That seems to me it would drive the power from what you said. Can you explain that a little bit more? Or?
Yeah, basically what we can, we've had the question that how does this relate to the angle at both the sending and the receiving end? And so the bottom line is the power flows as a function of the angle, and so this angle has to be advanced for the power to flow in that direction. But when we look at the reactive power and the angle, if we were to go through the corresponding equations for the sending end, we would see that the reactive power is actually flowing into the line from both ends as we separate the angle. That's a really good point, is that line becomes a huge consumer of VARs. And again, I want to show that back with the bungee analogy. This midpoint here is the voltage magnitude, okay, along the line. It's very accurate like that. So as we advance this angle, we have high voltage at this end, and so we have current flowing to the mid. And then maybe I can have Jay come on up here and we'll do this little demo together. Thank you, Jay. Just hold your end steady. As I advance my angle all the way to 180 degrees, I've got a fixed voltage, say of 500 kV here, a 0 voltage here. I'm going to have a huge current flowing in this direction. At this point, I've got 500 kV, but it's out of phase. But again, I have huge current flowing in this direction. So those huge current actually absorb VARs. The current drawn by that line is I squared times X. So that's the big difference to understand, is that that line can be a huge consumer of megavars when it is 180 degrees out of phase. Whereas we've talked about this before. A line by itself cannot absorb megawatts. Just a little bit of megawatts due to the I squared X. So no matter what conditions you're running that line at, it can only absorb a small fraction of the megawatts going through the line. But it can absorb huge amounts of megavars. And that's, transmission lines almost have this bipolar characteristic, okay? At light loads, they're actually generating megavars. This is a simplification. A transmission line actually has a capacitance because those conductors have a physical spacing. You can build up a charge on one conductor versus another. So based upon the voltage, you can get more and more megavars generated out of that line. So at light loads, it can be like a capacitor, but then at heavy loads, it turns into a very dominant inductive load. And you've got to really understand that. We'll get into that whole thing with what we call about the surge impedance loading. But this is really related to what can happen, especially as you go into, we get into what we call stability, and we get into the point where generators are oscillating and you're getting surges of power throughout the system. It's very important to understand these characteristics. So even if we don't go through all the math, I want you all to understand the basic characteristic of how the power flows versus angle. So we talk about megawatts flowing downhill on the angle. For megawatts to flow on that line, the angle at the sending end has to be more advanced than the receiving end. We talk about megavars flowing downhill on the voltage. In this particular case, what we did was we said, let's say the voltage of this is fixed at 1 per unit, because you really are controlling your voltages within a plus or 5% band. But we will vary the voltage magnitude at the sending end, and we'll assume that the delta, this is a case where there's no megawatts flowing, so we set the angle here equal to 0. Cosine of a 0 angle is actually 1, all right? So when we have 0 power flow in megawatts and 0 angle, this equation here simplifies down to the reactive power at the sending end is the voltage at the sending end squared minus the voltage at the sending end divided by the reactance. So this shows a characteristic that under light load conditions at least, megavars on a transmission line flow downhill on the voltage magnitude. And we see that here, all right? But as we increase the voltage at the sending end, we're putting more megavars down that transmission line. And so that's also an important characteristic to understand. But that's for a lightly loaded transmission line. That's the effect of the megawatts flowing in the reactance. But then you have to offset that with that's a simplification, because you have to offset that the fact that at light loads you have capacitors. Those capacitors will be pushing VARs out onto the system. And then as you have heavier loads, then this becomes an absorber of megavars. So you may have a positive voltage here. This may be 5% over nominal. This may be at nominal. But as you load up that line, the megavar effect of flowing from this end to this end, it becomes overcome by the fact that this becomes a huge consumer of megavars. In fact, we have a saying in power systems that megavars don't travel far, okay? And this is an example. It's very hard. You can ship megawatts from Milwaukee to Miami, okay? And you can plot it. You can put 100 megawatts into the system in Miami. You can put 100 megawatts into the system at Milwaukee, and you'll probably get like 80 megawatts out at Miami, and you can actually trace where that power goes through on the entire network from the source to the destination. With megavars, you just can't ship them over long distances, all right? That's because you you have other sources that are injecting megawatts, that are pulling megawatts off the system, and then you also have generators. Generators have an isolating effect. You can't ship megawatts past the generator, and we'll show that in the analogies we'll use later. So in general, like we said right at the start, the management of megawatts is a lot more complicated problem. It's nonlinear. You have sources all over the place. You have loads all over the place. But there are some underlying general rules. All right, so looking at a little more detail at a simplified diagram for a transmission line. Basically, there's a reactance effect because, like we said, those conductors have magnetic fields, and we represent that as a series reactor. Those conductors have a capacitance effect. You can have the conductors are in parallel, and based upon the conductors being closer and closer to each other, you can have a buildup of electrons on one versus the other. Again, all this is happening at 60 cycles per second. So we represent that by the fact that we have the actual capacitance is actually distributed all the way along the line, but we simplify that. We say that we have a capacitance at the sending end and the receiving end. We say that there's a total susceptance, which is the amount of net amount of conductance, and we divide it by 2. So what happens is when we have zero power flow, we're at light load, there's no I squared X loss in this. So basically we have a net contribution of capacitance charging on the system. So in that particular case, our system is absorbing the megawatts produced by those capacitors. As we load up the line with more and more megawatts along the bottom here, we load that line up, we get to a point where the net megawatts absorbed by the current through that reactance equals the megawatts produced by that capacitor. And so there's neither, the system doesn't have to absorb any, it doesn't have to produce any megawatts, and we call that megawatt value there the surge impedance loading, SIL. It's that loading, in this case 450 megawatts, where that transmission line is not producing or absorbing megawatts. But then look what happens. As we increase the megawatts, because we have the I squared X for megawatts absorbed, this goes up very much as the square of the megawatt loading. And we'll get into other situations where this is the case where we have voltages maintained at both ends. If we have a case where the voltage at this end starts to sag, this can actually go up as the cube or the quadratic function. So we can actually hit a point where we get tremendous megawatt absorption by our transmission lines as they get overloaded. And so that is a primary contributor to voltage collapse.